On a long flight at high altitudes, changes in the pressure will impact us less, since we are usually far from the ground. Continually changing the pressure setting in the subscale can be tiresome. As a result of this, we revert to a constant pressure setting. This is called the Standard Pressure Setting, or SPS. In the United Kingdom, this occurs when the aircraft climbs through 3,000 feet, when QNH is set on the subscale. This is known as the transition altitude. When passing through this altitude, we must set the standard pressure setting of 1013 hectopascals on the subscale. From this moment on, we refer to the indication on the altimeter as a flight level or pressure altitude. However, the transition altitude is not always 3,000 feet on QNH. For example, within the London TMA, it is 6,000 feet. In some countries, the elevation of the airfields can be greater than 3,000 feet. In this case, the transition altitude is usually a set height above ground level. Always be sure to check the transition altitude at unfamiliar airfields. When descending to an airfield, there will be a need to reset the altimeter back to QNH again. This point is known as the transition level. The transition level is not fixed and varies over time and place. As a result, air traffic will tell us at what level we should change from 1013 to QNH. Even when 1013 is set on the subscale and we are flying at high altitudes, we will still experience increasing or decreasing true altitudes as pressure varies horizontally. However, at such high altitudes, the change is almost insignificant. There is one final pressure setting. It is seldom used, and it is unique to very high altitude airfields. This pressure setting is known as QNE. It's defined as the height indicated on landing at an aerodrome when the altimeter subscale is set to 1013.2 hectopascals. This definition is only pertinent to those airfields where the normal QFE range can't be selected on the subscale. In other words, the QFE pressure values are outside the range 850 to 1050 on the subscale. We'll now look at what will happen when changing from one pressure setting to another. This is best demonstrated using a diagram. Let's say we have an aircraft with the airfield QNH of 1030 set on the subscale, and the aircraft is climbing through the transition altitude of 3,000 feet. The pilot will have to change the subscale to 1013. Notice that as the pilot changes the subscale, he is changing the zero datum point. As a result, the altimeter pointer will show a decrease in altitude as it moves anti-clockwise. Let's look at it another way. Now we have an aircraft which is descending through the transition level on approach to an airfield. The altimeter subscale would be set to 1013, but the pilot has been told by the air traffic controller that he must select the QNH, which is 1020. Notice that this pressure level is further away from the aircraft, and as a result, the altimeter's starting point is much lower. So, as the pilot adjusts the subscale, the altimeter will respond by showing an increase in altitude. However, it may be necessary to quantify these changes in pressure to actual values in feet. For simple calculations below 5,000 feet above mean sea level, we use a height change of 27 feet per hectopascal. This means that for every 1 hectopascal drop in pressure, the altimeter will show an increase of 27 feet. Looking at the diagram, we can see an airfield 1,000 feet above mean sea level. If the QFE was 980 hectopascals, what might the QNH pressure be? What we have to do is increase the pressure from the airfield to mean sea level. But by how much? If we know that pressure changes by approximately 27 feet per hectopascal, all we have to do is to find out by how much the pressure changes in 1,000 feet. This requires a simple calculation. 1,000 feet divided by 27 tells us that the pressure change in 1,000 feet is approximately 37 hectopascals. Now we simply add this to the pressure at the airfield to find the QNH. In this example, the QNH will be 980 plus 37, which equals 1,017 hectopascals. Let's try another example. Let's say an airfield 2,100 feet above mean sea level has a QNH pressure of 1005. What will the QFE be? Since the QFE is the airfield pressure, and the airfield is above mean sea level, then we know QFE will have a lower value than the QNH. But how much lower? If we know that in a height of 27 feet the pressure changes by 1 hectopascal, then we can say in 2,100 feet we have a pressure change of approximately 78 hectopascals. Therefore, the airfield pressure will be 927 hectopascals. So far, we've looked at how the altimeter works and how we can best use it to eliminate varying pressure changes along a route and near the ground. The variable subscale and the different pressure settings helped us to do this. However, there is one significant variable which the altimeter cannot cater for: temperature. In our earlier lessons on pressure, we saw that temperature affected the pressure lapse rate. Our altimeter is calibrated to an ISA temperature profile and is unable to adjust for the effect of any deviations away from ISA. Let's recap what we've already learned about how temperature affects the lapse rate and pressure levels. Here we can see that if we cool air down, the pressure levels contract and increase the pressure lapse rate. If we warm the area on the right, we can see an expansion of the pressure levels. Let's fly an aircraft from the area on the right to the area on the left at a constant indicated altitude. We know that to achieve this, the pressure must not change. In other words, we must follow a pressure level. However, in doing so, we are inadvertently following a pressure level that's actually descending. So in reality, we are descending, but the altimeter is not indicating this. Therefore, our true altitude is decreasing, but our indicated altitude is constant. There's a saying which is used to remind pilots of this potential problem. When flying from hot to cold, don't be bold. Or, even more dramatically, cold kills. We can further adapt this to be high, low, high. Flying from high temperature to low temperature, the altimeter will read high. In other words, it overreads the true altitude. We saw the use of high-low-high previously for horizontal pressure changes along route. This temperature effect will reverse if we fly into a warmer region. Notice how the aircraft is in fact climbing away from the ground, but that the indicated altitude is staying constant. This example illustrates the concept of low-high-low. Flying from a low temperature to a high temperature, the altimeter will read lower than true altitude. This temperature effect on the altimeter is important, and we must understand that in areas colder than ISA, our altimeter will overread true altitude. This, of course, only really becomes important when close to the ground, and especially so when a pilot cannot see the ground. His altimeter is not accurately informing him of his true height. So, to provide more accurate indications, we have a formula that enables us to calculate the error. This formula states that, for every 1 degree Celsius deviation from ISA, the error in the altimeter is 4 feet per 1,000 feet. This formula is derived from another formula we saw in the pressure lesson. That formula was telling us the height difference per hectopascal. The best way to explain this new formula is to go through an example. Let's say we have an aircraft that's flying level towards a very tall mast which is shown to be 2,000 feet above mean sea level. The temperature is 0 degrees Celsius. What would the altimeter indicate with QNH set? Firstly, we'll need to calculate the ISA deviation. Remember that at mean sea level, ISA states that the temperature is 15 degrees Celsius, and that it decreases by 1.98 degrees Celsius per 1,000 feet. The temperature at 2,000 feet above sea level, according to ISA, is 11.04 Celsius. The ISA deviation is therefore minus 11.04 Celsius. In other words, the real atmosphere is 11.04 degrees Celsius colder than ISA. From the formula, we see that for every 1 degree deviation we had a 4-foot error per 1,000 feet. But we have an 11.04 deviation. So we multiply 11.04 by 4 feet to give an error of 44.16 feet per 1,000 feet. However, our aircraft is at 2,000 feet, so we must multiply 44.16 by 2 to find the total error in 2,000 feet. Therefore, our altimeter is in error by 88.32 feet. If our aircraft is flying level with this mast, which has been shown to be 2,000 feet above mean sea level, then that must be our true altitude. But will our indicated altitude be more or less than our true altitude? If you remember from earlier, we said that in colder than ISA conditions, the altimeter would overread. Therefore, our indicated altitude would be 2,088 feet. The temperature error in altimetry is important and has led to a number of accidents. To prevent this, information is usually given to provide a landing pilot the necessary details to ensure more accurate calculations of obstacle clearance. Advanced instruments like radio altimeters very accurately calculate the aircraft height above the ground. Unfortunately, these instruments are only useful within 2,500 feet of the ground surface. Temperature errors are not the only errors in the altimeter. There are many more. However, these are outside the scope of the lesson. You will be made familiar with them when you study the altimeter in aircraft instruments.